So if we look at current over time, we're going to get an exponential decay. And the equation let's look up the equation. So that's like a constant times e to the minus t over rs. So again, it's exponential decay, where basically we always call rs times the time constant. So sometimes people will ask you again, what's the time constant? So then you have to take into account any resistance that you have and the exponential decay. And so if we have a small electrode, so let's back up for a minute. What's the biggest thing? What's the main factor that influences double layer capacitance? I've kind of said it a couple times, so hopefully it's obvious. What's the biggest variable in your experiment that's going to influence the size of your double layer capacitance? What?
Potential?
Nope, not potential. This is not. We will talk about potential in a minute, but we're not talking about potential. I give you electrode 1 and electrode 2. They're both carbon fiber electrodes. Which one's going to have the bigger capacitance? The bigger one. Size. It's all about area. And again, this comes from the capacitor equation. The bigger the plate, the more charge you can store. So the main factor that influences is absolutely size, right? So it scales. The bigger your electrode, the bigger your double layer capacitance. Okay, I didn't tell people, but maybe you already know this, probably you don't. If you took my class, you should. In one time constant, so 1 RC, one time constant, your signal should drop from an absolute value of 1 to about 0.37. So you lose about 63% of your signal in one time constant. So if we have a big, let's say we have a big electrode, do we have a fast decay or a slow decay? Slow, right? We have a slow decay, right? So if we have 2 electrodes, right? We might have small and, well, that's a terrible exponential decay, right? But the, relative graphs would look like this. Small and big, right? So a big electrode, not only does it have a bigger capacitance, it also takes longer for it to dissipate, right? For the current, that nonFaradaic current to dissipate. So again, I'm just trying to get this in your head. We work with tiny electrodes. That's a huge advantage for background charging current. If we wanted to wait out the charging current, we actually can. That's called primary ground. We don't do it that often. But we could wait it out because our electrodes are small. If you get a huge electrode, it's really hard to wait out. It could take a while for it to dissipate. So size matters. The smaller electrode you get, yes, the smaller double layer capacitance, but also the less time it takes for the ions to rearrange. Okay, so let's talk for a minute about what double layer capacitance means for cyclic voltameter. We're just going to do a voltage. All right, so let's say this is our voltage, our applied voltage. Right, so this is my definition of like our ramp, right? We go up, we could start at some initial potential, right? Initial voltage, you don't have to start at 0. You can start at 1, you can start at -0.4, you have to do that a lot. It's such and such, right? So I'm not trying to imply that you have to start at 0, and you go up. The voltage then, again, if we think about this circuit now, I've reduced it to resistance of the solution and then a double layer capacitance term. And so the voltage is dropped both over the resistor and over the capacitor. All right, so we could write an expression over here that the voltage is equal to whatever this initial voltage is, plus V times T. Little v, and I'll try to write it little, right, is what we use for scan rate, right? That's in big volts per second. So sorry, it's hard sometimes to distinguish that. Little v is scan rate, not voltage. That's not big V, that's little v. Right, so, all right, well, we start here at some, initial voltage, we scan up, right, at a given rate over time. So that would be defined. So I'm going to plot this in the left-hand side of the equation. Okay, so the voltage applied over a resistor, again, I'm going to skip a little bit, although if you took my class, these two look somewhat familiar, is the resistance times dq dt. dq dt is another way of looking at, is another way of defining I. So this ends up being IR, that's the voltage times the resistor. But I'm going to write it as dq dt, so we can solve it in a minute. And then resistance of, voltage drop over our capacitor, we've kind of already defined. So that's charge over, again, this is big C. And charge. And if you were to solve this with these assumptions, let's assume that we're going to start at 0. So I don't have some initial value because I don't want to deal with that. And let's assume that Q is equal to 0 at time 0, meaning we don't start with any charge in the electrode. We're going to start at 0 volts, no charge in my electrode. We're going to ramp up, we're going to go. Then the expression for the double layer charging current is this. Little v, that's scan rate, times double layer capacitance, times 1 minus, e to the minus t over r. I'll do it that way. Okay, so what that says, let's look at this. So 1 minus an exponential, right? So this, I don't have to do it there anymore, right? 1 minus an exponential decay gets you this, right? 1 minus an exponential decay gets you that, right? So it's just the curve going up rather than coming down. 1 minus it is the curve going up. I think you probably could have figured that out that time. So that's a real common curve that we see all the time, 1 minus an exponential. Okay, so this is the kind of shape that we should get. All right, let's do some math again. The book does a lot of math. I'm not going to do every math, but I'm going to put out the equations I think are useful. What's the height of this? Like, what's the maximum that this reaches? From the equation, what's that height? VCD, right? So this out here, right, sets the height. That's going to set the amplitude, right? So V times CD sets the amplitude. So what is the amplitude of the double layer capacitance affected by? Well, we talked a lot about double layer, about the charging current. The amplitude of the charging current. So now this is a plot of I, and so this is a plot of that. So, okay, so it has to do with the double layer capacitance. It also has to do with the scan rate. So if you do that scan rate that everybody does when they first come in the lab, maybe people don't actually look at the background charging current, right? But you might tell it with the gain if you have to change your gain setting, right? Your background charging current goes up and up and up because the fundamental equation tells you it should go up and up and up. That it depends, as I said, if you solve this equation, integrate it, you get out that. So there we get scan rate in there. And then again, as I said, this double layer charging current depends primarily on area. Okay, so we've discovered that this is what it looks like if we go up. Turns out if we go back down, it should kind of look like this. So the background charging current for our electrode should look something like that. So Does our background charging current look like that? No. Right? I think most of you in the lab would know what a background charging current looks like. I would draw my best approximation of the waveform that you see. Right? That's what you get off the oscilloscope. I could put it back over like that, right, and make it look like a CD, but this is not what it looks like in time, right? So I'm just switching between time and potential. So that's approximately what it looks like. So why does it look like that then? I just told you we should get, again, a 1 minus exponential decay, and that's null, we get it off. So there's got to be something else going on. Anybody know why the background doesn't look? Again, the textbook tells you this is what your background should look like, and our background doesn't look like that. So this is where we have to deviate from the textbook. Guesses as to what's going on? Have you read any papers about the background charging current this summer? No. All right, does anyone know anything about what happens at the carbon surface of the electron? As we scan up in voltage, does anything happen to the surface? What's happening to the surface?
Creating more surface oxides.
You're creating surface oxide groups, right? And so as we're creating surface oxide groups, or even if they just exist in the first place, we can do Faradaic reactions with them. So what our background charging current really looks like, not the color, it really looks like this. This is the, I'm just trying to approximate, that is what happens due to double layer capacitance, right? So there should be, you know, this, but what we have in our lab, right, colors, right, this. So this is what it should look like according to the textbook. And what we really get in our lab is something like this. Right, that's really dramatic. I won't get off the top part. I can't see the drawing unless I draw it like that. Right, but we get these extra features, and these extra features have to do with either surface groups that are oxidized or reduced, or perhaps, even if we get out here, if we go out too far, right, these are Faradaic reactions. They're like, you know, reducing water, oxidizing water, that can happen at certain potentials. So you can't just say it's all double layer capacitance. Those surface reactions are actually Faradaic, so it's kind of weird to call them non-Faradaic. Again, there may be, but they're not what we want to see. They're the same every time, hopefully, kind of thing. But I want you to know that your background should look. Now, we all know what a good carbon fiber microelectrode should look like, right? And we like that curvy stuff on it, right? A good person gets into knowing what it should look like. And you say, I like those curvy stuff because that means it's, you know, but what you're really looking at is how well the surface is covered with surface oxides. And, you know, the overall magnitude of the current tells you about the double layer charging current, but how much you get those extra dips and curves and all of that, that's all has to do with surface processes. That's not just double layer. So double layer is just this 1 minus thing, as I said. And so what you have is kind of on top of that, you have surface reactions. And again, that's something that people just, I think everybody kind of learns in the lab what it should look like in our situation, but they maybe don't understand that it's probably two things combined. Faradaic reactions of surface groups, which we're not really interested in characterizing, but they're there, and then the non-Faradaic things as well. Okay. Let's talk really quickly, just in case you have to meet these applications. Hurrying along. There are two definitions that, again, if you ever take, and you might have seen these in undergrad as well. They always are talking about these definitions in the textbook. So in a galvanic cell, a reaction occurs spontaneously and converts what they call chemical energy. So it converts something chemical. What's chemical energy? Like bonding energies. You know, like where's energy stored in chemistry? It's stored in bonds to electrical energy, i.e., right? So this is like, right? And this is like bonds. So you break bonds and you make a current, right? That's, you know, and if that happens spontaneously, that's called a galvanic cell. The opposite of that is an electrolytic cell. In an electrolytic cell, you must add energy to get it to go. So right, you could put your electrode in there, but if nothing spontaneously happens, you have to add energy to make it go, to make your electrochemical reaction go. That's an electrolytic cell. So when we look at dopamine, let's say in the brain, what kind of cell do we have? We're a galvanic cell or an electrolytic cell? If I just plop an electrode into the brain, what am I going to see anything? No, right? I've got to add energy, i.e. I have to change the potential to get it to go. So everything we do in our lab is electrolytic cells, again. But I just want you, what I'm hoping to teach you is something that I've learned that all big scientists do, and that is everything they read, then they try to interpret in light of what their own experiment is. So, you know, you read these texts, they're snoozeworthy, right? Definitions in the textbook. But then try and challenge yourself, wow, what do I do? If there are two different things. Now, a galvanic cell, right, is often, you know, referred to as a battery. We don't have a battery, right? We're not making energy. And so we're looking at that. Okay, I'm going to try to do just a little bit more. Yeah, sorry, I'm going slower than I thought, but that's not necessarily bad. I'm going to make you a big chart. I'm going to make you this big chart so that I feel like I get everything in. Again, this chart could like be the outline of the textbook, quite frankly. All right, so we're going to look at variables that affect electrochemistry. And so we can classify these variables into various categories. So electrical variables, things that are going to change in electrochemistry, right? We already talked about some, right? We talked about potential, so we could change the voltage. We talked about current, right? We could have different amounts of that. We've talked about charge. So some methods will look at charge and that kind of thing. So these are things, we're going to see these variables a lot. That we can kind of manipulate around. All right. So, all right, so that's the easy stuff, right? You know, stuff that we see all the time. External variables, right? So these are things like temperature, right? So that could affect your electrochemistry. Pressure, not that we do a lot of high pressure electrochemistry or whatever, but I mean, again, think equilibrium. Anything that could affect equilibrium could affect your electrochemistry. Also, we'll put in time. Again, time matters a lot in electrochemistry. If you're measuring current, it's something that happens over time, so we can't get away from time. You know, we do scan rate, that's time, as far as that goes. All right, another category of stuff that can vary in electrochemistry is electrode materials. Well, I didn't mean to say I meant to say variables. Because the first one is whatever the material is. So we already saw an example of that reduction of H plus varying based on the electrode material. We can vary the surface area of the electrode. We talked about that with double layer capacitance. Something we haven't talked about up until this point. We can vary the geometry of the electrode, right? In our lab, we use disc electrodes and cylinder electrodes, but there are many more geometries. Hanging drops, bands, arrays, you know, all sorts of things, right? And that's going to affect what kind of signal you get. And then we're going to lovingly call it the surface condition, right? We all know in our lab about things like surface fouling or surface oxide groups or, you know, what's going on at the surface, lots of different variables that can happen there. Okay, so what your electrode is can change electrochemistry. We'll talk a little bit about mass transfer. I think that's chapter 4. So the mode of mass transfer can affect it, whether you're using diffusion or convection. Again, for mass transfer, what we really care about is what we end up for surface concentration. And under mass transfer, I'm also going to put on absorption, whether or not something sticks to our electrode. That all kind of goes in the same thing, and we'll get to, unfortunately, a diagram where we kind of like try and link all of those together. And then, right, the final thing for all of our solution variables, right? So here we care about what's the bulk concentration of our analyte that we want to look at. That's what's going to come into play. We can look at the concentration of other species, particularly the electrolyte. So what's in the electrolyte? That might affect the signal that we get, and the solvent as well. So as I said, this is why you can write a whole book on electrochemistry, because you can start off with a very simple, like you should be able to look it up in the table, what E0 is based on like energetics. And then, you start looking at all of these different variables that kind of go into what you're actually going to get out. And that's why it's kind of... Okay, so coming tomorrow, we will do a little bit on equations. We will talk about mass transfer and 3 electrode systems. Sorry, it's not really good there today. And then we'll do chapter 2 and 3, although I don't cover those very deeply.